Hey everyone, and welcome to our cinematic 3D digital studio. Today, we are jumping right into a really fascinating visual explainer, a journey that completely bridges the gap between stunning aesthetic art and the deep underlying mathematics of infinity. We're going to explore exactly how seemingly complex infinite shapes are actually built from incredibly simple repeating rules. If you've ever found yourself wondering how the universe is structured on a fundamental level, well, you are in exactly the right place. So here's a quick look at our roadmap for today. We'll start with art and infinite spirals, move on to defining proper self-similarity, then build the golden fractal tree. After that, we'll check out the Koch-snowflake boundary, tackle the Hausdorff dimension, and finally wrap things up with fractals and biological systems. All right, first up, art and infinite spirals. Before we get bogged down in the math, we really need to see what this concept of infinity actually looks like. Take a look at this massive, brilliantly lit 3D spiral sculpture by the artist Arend Nijdam. What's truly mesmerizing about this piece is how the sweeping, golden arcs are entirely made up of tiny, identical arcs. As your eye travels down the spiral, you realize that the overarching structure is built by just repeating its own shape on a smaller and smaller scale. It feels totally endless, right? Yet, somehow, it's contained perfectly right here in a single visual space. This visual phenomenon actually has a beautiful historical parallel. Take a look at this quote from the 18th century scientist and mystic Emanuel Swedenborg. He wrote, "A fractal is an object where the greater elements are arranged like the parts, and the parts like the greater elements." Now, historically speaking, Swedenborg was actually talking about his concept of the structure of heaven when he wrote this. But honestly, his words perfectly hit the nail on the head when defining the mathematical reality of what we now call fractals. Moving right along to Section 2, defining proper self-similarity. Okay, so transitioning from the world of art and philosophy into the strict mathematical rules that govern these mesmerizing shapes. The absolutely crucial concept we have to grasp here is proper self-similarity. This is literally the engine that drives a fractal. In plain English, it simply means that a shape contains a perfectly scaled down, smaller copy of itself. It's not just a vague symmetry, guys. It's a strict mathematical similarity where a smaller part of the object is a perfect miniature clone of a larger part of that same object. But how do we actually build these complex objects? Well, we definitely don't try to draw them all at once. Instead, we use a real workhorse of a process called iteration. Iteration simply means starting with a basic shape and repeatedly applying a single, carefully chosen transformation over and over again. After every single step, the object gets closer and closer to exhibiting that perfect self-similarity we just talked about. To get a true, complete fractal, you would theoretically have to iterate infinitely many times. And yeah, good luck trying to do that by hand. That brings us to Section 3, the golden fractal tree. Let's actually see how this builds by constructing our own fractals step by step. We are going to grow a mathematical tree using literally just these 3 simple rules. Step 1. We start with a plain vertical line segment. That's our trunk. Step 2, we branch the upper part of that line into 2 new parts, angled perfectly at 60 degrees on both sides. And step 3, we take those new branches and apply exactly the same rule, repeating the entire process infinitely. Now, looking at these initial stages, we see our basic vertical line segment sprouting its first sparse sets of those 60-degree branches. It doesn't look like a whole lot just yet, does it? But it is already starting to exhibit that intriguing self-similarity. If you look closely at it, the right-hand branch, together with its smaller sub-branches, is already starting to look like a tiny copy of the whole tree. Fast forward a bit, and this brilliantly illustrates the sheer complexity that arises after many iterations. Here, we're seeing the result after a deep buildup, around 12 iterations in. The self-similarity is absolutely undeniable now. But there is a catch here. If we aren't incredibly careful with how long we make those new branches during each step, things get real messy real fast. If the ratio of the new branches to the parent branches is too large, say 0.65, the branches wildly entangle and overlap with each other, completely ruining that clean, beautiful structure. So, to prevent that messy entanglement, we have to scale the branches using a very specific mathematical sweet spot. Think about it. What should the ratio of the lengths of the new branches be so that the tips exactly touch without overlapping? The magic number is roughly 0.618. Mathematically speaking, that exact sweet spot is 1 divided by the golden ratio. When we apply this specific 0.618 ratio to the length of our branches, the branch tips touch perfectly in this beautiful geometric harmony. It's like a giant puzzle locking perfectly into place. We literally get to see the famous golden ratio in action, organically organizing the infinite complexity of our tree. All right, let's jump to section 4, the Koch snowflake boundary. Next, we're pushing this concept of infinite scaling to its absolute mathematical limits, moving from our tree to something called the Koch snowflake. And this brings us to a seriously fascinating question to ponder. How can we possibly measure the boundary of a shape that never, ever stops iterating? With our tree, the branches just got smaller and smaller. But with a shape like the snowflake that keeps growing smaller triangles on its edges infinitely, the perimeter effectively becomes infinitely fuzzy. Take a close look at the Koch snowflake right here. When we zoom in, or rather, if we triple the size of the snowflake, we can map a large chunk of its jagged boundary perfectly back onto a smaller section of itself. Because a similarity transformation maps the boundary within itself, this actually proves it is a complete fractal. But as you might guess, this infinite recursive fuzziness creates a huge headache for standard geometry. Which leads us right into section 5, the Hausdorff dimension. To actually measure this infinite fuzziness, we have to completely rethink how we define dimensions altogether. We are stepping way out of our familiar 1D, 2D, and 3D worlds here. Scientists and mathematicians use logarithms of size and number increases to calculate a shape's dimension. Check out this comparison. If you double the size of a standard square, its area is made of 4 original squares. The formula is log 4 divided by log 2, which gives us a flat, perfect integer of 2. It's two-dimensional. Pretty standard, right? But if we triple the size of our Koch snowflake, the number of line segments increases by a factor of 4. So the formula becomes log 4 divided by log 3. And when you actually divide log 4 by log 3, the math spits out exactly 1.2618. This is just incredible to me. It means this object's boundary doesn't exist as a simple 1D line, and it's not a flat 2D surface either. It exists in a fractional dimension, specifically called a Hausdorff dimension. It is quite literally a shape of a fraction of a dimension. Finally, let's look at section 6, fractals in biological systems. So you might be wondering, why does all this incredibly abstract mathematics actually matter to you and me? Is it just a neat trick? The answer is absolutely not. It is deeply, fundamentally tied to reality. While mathematical fractals are abstract infinite iterations with perfect geometric dimensions, scientists have discovered something truly remarkable in nature. The metabolism of many living organisms basically behaves in ways that perfectly mirror these exact fractals with non-integer dimensions. The abstract math just built step by step is quite literally operating inside living tissue right now. Which leaves us with one final, truly profound question to close out our explainer today. Are these golden, infinite rules of mathematics not just abstract concepts, but the very blueprint for life itself? When we look at art, or trees, or snowflakes, we might actually just be looking in a mirror at the fundamental code of nature. I really hope this visual journey has completely changed the way you look at the world around you. Stay curious, keep exploring, and always look for the infinite details hiding right in plain sight.